Dear classmates, welcome back to the logic simulation. In this video, we are going to introduce the last logic simulation technique, the parallel simulation technique. The idea of parallel simulation is very simple. We try to pack W patterns into a single word, where W is equal to the CPU word size. In this way, we can simultaneously evaluate a gate with W patterns. This idea exploits the inherent parallelism of bitwise logic operation. In this following circuit example, where W is equal to 4, we pack 4 patterns into a single word. For primary input A, in the first pattern it is 1, in the second and the third pattern it is 0, in the fourth pattern it is 1. If we perform a bitwise operation, we can simultaneously obtain the result of a gate output. For gate G1, we can perform a bitwise OR operation, and the output of this OR gate is 1, 1, 1, 0. And we perform a bitwise AND operation, so the gate output of G2 is 1, 0, 0, 0. In this way, we can obtain the output of the circuit, which is 0, 1, 1, 0. Please note that in this parallel simulation, we consider only binary logic. That means we ignore unknowns or high impedance. So this is a simple quiz for you. What is the speed up of parallel simulation? Suppose that the CPU word size is W. Is it W or W squared, or no speed up? The answer is simple. We can have linear speed up W over traditional simulation. In practice, we need to consider more than binary logic. So how about ternary logic? A simple idea is to use 2 bits to represent a node. For example, we can use 1, 1 for logic 1, 0, 0 for logic 0, and we add 1, 0 for a node. This idea works fine with AND gate or gate, but it has some problem with inverter. For example, we can use 2 bits to represent one pattern. So the first pattern is 1, and the second pattern is unknown. After bitwise operation, the output of OR gate G1 is 1 and U. This is the correct answer. After the inversion, we will get 0, 0 and 0, 1, which is undefined in our encoding system. If we perform a 0, 1 with 1, 0, we will get 0, 0, which is a wrong answer. From this example, we can see that we cannot use both 0, 1 and 1, 0 as unknown. It does not work very well. A very simple solution is to improve our encoding method. In this improved encoding method, we use 2 words to represent one signal. For signal A, we have A1 and A0. When A1 equals 1, it means a logic 1. When A0 equals 1, it means a logic 0. When both A1 and A0 are 0, it means a node. For the same circuit example, now we have 2 words for primary input C, we have C1 and C0. 0, 1 represent a logic 0. 1, 0 represent a logic 1. And the 0, 0 represent a known. So, how do we use this encoding to evaluate a gate? In this table, we show how do we evaluate a gate using the improved encoding. For example, for this AND gate, we have A and B as gate input, C is the gate output. We can use a bitwise operation to obtain the output. C0 is equal to A1 bitwise and B1. And the 0 is equal to A0 bitwise or B0. The reason is that output is 1 only when both A is 1 and the B is 1. On the other hand, output C is 0 when either A is 0 or B is 0. In the same way, we can write the equation for the OR gate. C1 is equal to A1 plus B1. And C0 is A0 and B0. We can see the dual relationship between the AND gate and the OR gate. When we have an inverter whose input is A, output is C, we can simply exchange A0 and A1 to produce C1 and C0. So we have a short quiz for you. Please write the equation that can evaluate an exclusive OR gate in parallel. Have you got it? Yes. For exclusive OR gate, we have two scenarios where C1 can be 1. That is, A is 1, B is 0, or A is 0 and B is 1. For C to be 0, we can have A1, B1, or A0, B0. This is our answer. So how can we evaluate this circuit in parallel? We can apply the equation that we have in the previous slide to generate the output for each gate. And for this inverter, we can just swap those signals. So the correct output is now 0, 0, unknown, and 1. In conclusion, what is the complexity of logic simulation? Suppose that there are P patterns and G gates. The compiled code or parallel simulation complexity is theta P times G. For event-driven simulation, it's theta P times E, where E is the number of events for each pattern. If we assume that the number of events is OG, then again we can have OP times G complexity. So this is a good news because logic simulation is a polynomial time complexity. So logic simulation is quite a simple task in EDA area. In summary, we have introduced parallel simulation in this video. It exploits the bitwise parallel operation to gain linear speedup. If we want to improve the encoding for a node, we can use two words to represent one signal. Finally, we show that logic simulation needs polynomial time complexity. Now we compare the three simulation techniques. Compile code simulation is quite simple, but the problem is it is slow and it considers only 0-gate delay. Compile code simulation can be used for cycle-based simulation only. The event-driven simulation considers the gate delay. However, the algorithm is more complicated to implement. The parallel simulation is simple and fast, but it only considers 0-gate delay. So now we have a final FFT for you. Can we swap the pairs after each inverter? If we want to use 2 bits for encoding, for example, 1, 0 represents a U. After the inversion, can we simply swap these 2 bits so that we can obtain a correct U again? So same thing here. If we swap the 3rd and the 4th bit of output K, then we can obtain a correct output. If it does work, what are the advantage and the disadvantage compared with the encoding method that we previously taught in this video? These two are interesting questions for you to think about. Thank you.